Okay, so let's talk a little bit about how we would represent these visually. Okay, first of all, the magnitude we represent by the length. Okay, so even though these are all going different directions, this one is longer than the other two. So we would say it has a greater magnitude. Okay, so if all of these were representing different velocities, this one would be going faster than these two because it's longer. Okay, the better, you do not have to get out a ruler and draw everything exactly to scale, but the more close to scale you can draw them, the better. All right, so if you have two different velocities and one's 25 and one's 50, draw the 50 about twice as long as the 25 one, and that'll help you get a better idea of what's happening. Okay. Also, the slope of a vector, which we use to find the direction or the direction angle, okay? We're going to look at this notation here. This is what's called the component form. And really it's breaking down a vector into its horizontal and vertical movement, okay? But our slope, you guys know from pre-algebra that slope is rise over run, okay? Well, B is our vertical, our rise, and A is the horizontal component. So the slope is B over A. And then we'll see later on how to get that actual direction angle. But we could talk about the direction of a vector in terms of its slope. Okay? Another term here, parallel vectors have the same or opposite directions. So you see here, the arrowheads are going opposite directions, but they're never going to intersect, okay? So these are still parallel. That's one thing that students sometimes forget. They don't have to be going the same direction, they can also go opposite directions, and we still consider them parallel, okay? Another term is equivalent vectors. Equivalent vectors have to have the same direction and magnitude, okay? So they can't be opposite. They have to be the same direction and the same magnitude. And if you're drawing them, you would try to draw them as close to the same length as possible. Okay? So again, just some more terminology here as we introduce this topic. Let's talk about vector addition. Okay? If I am adding two vectors together, we're going to look at adding in two different ways. One is graphically, all right, and the other is with the components once we look at component form, okay? So if I'm adding these vectors graphically, what I would do is I would, first of all, if I want to do u plus v, what we're looking for here is what's called the resultant vector, okay? The resultant vector is like you're following directions. When you're doing vector addition, it's kind of like when you look at Google Maps and you get directions to go somewhere and it says, you know, turn left onto this street and drive 5 miles, and then turn right onto this street and drive another 3 miles, and so forth. Okay? If I follow those directions, okay, my end result is hopefully getting where I wanted to go. That blue line is what I want to do. However, there's not a street directly from my house to where I want to go, so I've got to follow these other directions. That's like what vector addition is doing. It's giving you the directions to get the result that you want, or it's how you find the result after following certain directions. Okay? Yeah, we'll do it with numbers actually more often, but I want you to get a visual idea of what's going on here too. Okay? So if I wanted to do u plus v, what I would do first of all is I would draw vector u like this. Okay, so there's vector u. And then, just like you would if you were driving and following directions, I go from wherever I ended up, which is right here, and then I'm going to go along this vector v. Okay? So vector v is about at this angle, and it's about this long. Okay? There's my vector v. So the resultant vector is that I started here and I ended up here. Okay? Now, we could say a lot of things about this. We're talking about this in terms of motion, all right? But remember that these are vectors. They can represent numerous things, okay? It could be that we drove along this street and then we drove along this street. We had two different displacement vectors. We have direction and a distance, okay? So in the end, we ended up literally moving from here to here as a result. But this could also be something like this. Let's say that there was a river flowing with this velocity, and we were trying to swim this direction. Okay? Well, just because we're trying to swim this direction like this doesn't mean that our body is actually going to go that way, right? Because the river here in this case is pushing us to the left. So if we tried to swim and the river was pushing us this way, the end result is our body would actually move this direction through the water. Our velocity, our resultant velocity, would be this. Okay, and we'll look at problems at how to figure out what that would be later on. Okay. This could also be two different forces. Maybe one person is pushing on something with this amount of force in this direction. Another person is pushing on the same object but pushing it this direction with a little bit less force. Where is that object going to move? Well, it's going to move along that path with a certain amount of force. That's the end result. Okay? And guys, this is important as we study vectors because if we're looking in physics, there are entire studies of physics. One's called dynamics, which is the study of imbalanced forces or motion. Okay? And there's another called statics. Statics is when we don't want something to move. So we have to balance all the forces. Like if you're designing a bridge, you've got to have all the forces balanced so that the bridge isn't going to fall down, it's not going to lift up, it's just going to stay put. Okay? Now, another thing that we can do is called scalar multiplication. And really, if you think back to your days of elementary school arithmetic when you learned how to multiply, that's all this is. It's simply vector addition. So if I had 3u, I would do a u, and then I would do another u, and then I would do another u. Okay? So there's u plus u plus u, and that would give me 3u. So there is 3u. Now notice here the direction stays the same, but the magnitude obviously gets multiplied by whatever the constant is. Okay? So, we visualize these a lot. Let's talk about the components. All right, this is what we're going to deal with the vast majority of our time, but being able to draw things is going to be helpful as well. Okay? So, one challenge with vectors is the fact that there's like 4 different ways of notation when it comes to vectors. Okay? And the component form is this notation here. Okay? We can look at regular parentheses like you see here. Okay, you can see parentheses like this, but notice the components are top and bottom. Okay, this is not a fraction. There's no fraction bar in here. It's simply A is our horizontal component and B is our vertical component. Okay? Or we have these brackets here, these kind of angled brackets. Right? Now I will tell you, these are used more commonly than this in a lot of things, because what could this easily get confused for? Coordinates of a point, yeah. That's something that as you're doing different problems, you're going to have to pay close attention to. And by using different notation, it'll help you keep them straight within a problem. Okay? Now, one thing that is a little bit challenging is that if we're in a situation where we have an origin and we have different points, we can actually write a point like this, the point 2, 3. If you think about it, if you look at the origin as your starting point, you could write a vector to get to point A. We need to go over 2 and up 3 to get from the origin to point A. Well, then we could call that position vector 2, 3. Okay, it's the position of point A relative to our origin. Okay? But as though 3 versions weren't enough, there's a 4th way we can write vectors as well. And by the way, IB uses all of them. Okay, so you should be familiar with all of them. The 4th way is unit vector form. Okay, unit vector form, and you'll see it something like this: A times I plus B times J. And notice the I here is a vector. It's in bold, but it's a little hard to see. Okay, that's vector I, and here's vector J. Okay, so there's vector J. A and B are simply the numbers that make up the components. And the reason why I and J are called unit vectors is because I is the vector 1, 0, and the length of I, or the magnitude of I, is 1. That's why it's called a unit vector. 1 unit, just like the unit circle has a radius of 1. Okay? J is the vector 0, 1. It has a magnitude of 1 as well. Okay? So by writing it this way, we're really breaking it down into a vector addition problem with those scalar multiples. Okay? So if I were to look at this vector 3, 5, okay, here let's say we have this velocity and angle that something gets shot up into the air with. Okay? If the horizontal component is 3 and the vertical component is 5, we could write it any one of these 4 ways. Okay, and those all represent the same vector. Okay, does that make sense? Does that make sense? Okay. I know we're dealing with a lot of different stuff here just in this first lesson, but we're kind of giving you a crash course to get into all the notation and terminology and stuff that we're going to be using for this whole unit. Okay? So here's the cool thing about component vectors. I know I told you that if we have a coordinate plane, we can write a point as like a vector from the origin to that location. But the cool thing about this is that we actually don't have to have coordinates. We just have to have kind of a set unit of measure to make coordinates of. All right? So for example, if I wanted to write vector BA, basically I'm asking, hey, what are the directions to get from B over here to A? All right? And if I were to draw that, okay, vector BA, I need to go 4 units to the left and 1 unit down. Okay? So if I'm writing this as 4 units to the left and 1 unit down, what would my horizontal component be if I'm going 4 units to the left? Yeah, -4. And if I'm going 1 down, what's my vertical component? -1.
You don't put negative?
Yeah. Sorry, I didn't write that. So -4, 1.
-4.
Okay? If I wanted to get from B to C, I go 1 to the left and down 1, 2, 3, 4, 5. So that would be the vector what?
-1, -5.
-1, -5. Good. Okay?
So then DC would just be 2.
Okay.
2, 0.
Yeah, there you go. If I want DC, that's going to be the vector. I go 2 to the right, so it's +2. And I didn't go up or down at all, so it's 0 for my vertical component. Okay? I could do AC. I go over 1, 2, 3 and down 1, 2, 3, 4. So it's 3, -4. Okay? Now, I want you to think about CA. Okay? Think about CA here. Okay? It's -3 and +4. Notice here that AC and CA are the same 2 points, right? We're just going opposite directions. And what happened to the components there?
They reverse their sign.
They reversed their sign. And that's because AC is the opposite of CA.
Wait, also for DC, did you put a 0 after the 2?
For DC? Yeah. Okay. So AC is the opposite of CA. If it's the same 2 points, just opposite direction, then you can just make the coordinates the negative. It's kind of like, again, if you have directions written out and it said take a left and then take a right, if you want to get back where you started, then you've got to go opposite, you know? You've got to go left and then you've got to go right on your way back. So if it was left, left, right to get there, you got to go left, right, right to get back home. You just do the opposite. Same thing here. Okay? Just to close this out, let's go ahead and do DB. What are the components for DB? +3 and 1, 2, 3, 4, 5. Good. Okay? So that's what's cool about this. You don't need coordinates. As long as you have some kind of a grid or some kind of a unit of measure that you can use to work with these, okay? However, what do you do if you do have the coordinates, okay? The nice thing is if you do have the coordinates, you don't actually have to draw it. You can figure out, in this case, we have point A, -4, 6, and point B is 5, 4. Okay? So, I simply subtract the x coordinates to get my horizontal component, and I subtract the y coordinates to get my vertical component. Now, I will warn you, the number one thing students do with this is they have the direction going the wrong direction. Okay?
The first one minus the second one, so A minus B.
Actually, it's reverse. That's why people mess this up. You take the coordinates of the point you want to go to, and you subtract the coordinates of the point you're coming from. Okay? So, we want to go to going to B, and we're coming from A.
instead of like the midpoint formula, where it's like y2 minus y1 and x2 minus x1.
Oh, the slope formula, yeah, it's kind of it's very similar to the slope formula, because if you think about it, that vertical component is telling us the distance we go up and down. That's our rise. And the horizontal component is how far we're going left or right. That's our run. So rise over run, here we just have it written a little bit differently. So vector AB in this case is going to be,
9, 10.
let's do it with the brackets to distinguish from the parentheses. We would take the coordinates of B, so 5 and 4, and we're going to subtract the coordinates of A. So 5 minus a negative 4, 4 minus a 6, and we get 9, negative 2. You can obviously see how drawing it might be helpful, even though we don't have to. We can see it's going down, because as we go from from A to B, it's going down 2, so negative 2 for our vertical, and we go from A to B is 9 units to the right, so that's why we have a positive 9. Okay? So the last thing that we have here is a concept we talked about earlier, and we saw the notation for this earlier, but magnitude, okay? Magnitude of a vector, all right? And if you think about this, it makes total sense. What am I using? When you see this, I mean, I know we haven't ever used this notation before, but what does this kind of look like? You have something squared equals something squared plus something squared. What?
A squared plus B squared, C squared.
Yeah, the Pythagorean theorem. Okay, the Pythagorean theorem. That's behind a lot of stuff that we do in vectors. It's behind all of our right triangle trig and everything. Here it shows up again, the Pythagorean theorem. If we have these horizontal components, like for example, this vector v here, if I had negative 3 as my horizontal component, and I had 4 as my vertical component, to give me this vector v, okay, I can treat this as a right triangle, and notice the lengths of the sides are negative 3 squared plus 4 squared. And if I just do it that way, it's going to give me my magnitude squared. So I square root the whole thing, so it just gives me the magnitude. Okay? So the magnitude in this case is what? Do you know your special right triangles? 3, 4,
Oh, 5.
5. Yeah, this one's actually a 3, 4, 5. And by the way, magnitude is a measurement of length or size, so it's always going to be positive. You're never going to have a negative magnitude. Okay? So, this is our groundwork for everything we're going to be doing this whole unit in vectors in 2 dimensions. In a couple of days, we're going to throw in third dimension. Okay? And then after that, we're going to throw in the 4th dimension, time. And things get real fun, because we deal with parametric equations and actual motion and stuff like that. And that's actually a good bit of where IB focuses their study of vectors on, is on those parametric equations and equations of lines.
It's parametric.
We incorporate, we look at our x and y and even z if we're in 3 dimensions motion as separate equations relative to time passing. Okay? As opposed to just looking at, hey, how much does y change as x changes? we're gonna look at how much does y change as time passes and how much does x change as time passes. And we'll get there. Parametric is, well, we can do it in 2D, we can do it in 3D, but
It's basically 3, like.
we could use, we could do everything in 3, so.